I done? So yeah, here the problem was like, okay, sonoluminescence is some emission of short bursts of light from imploding bubbles in a liquid. And this effect is not really known for now. We don't really know exactly what is happening in there, but the question was suggest a setup to observe the phenomenon and study the spectrum of the emitted light. And can this effect be used to obtain some coherent laser-like emission? So, to try to answer these questions, I will first explain the sonoluminescence principle with, like, first a bit of theory, like how can you trap the bubble, how the bubble behaves in the liquid, how it's possible that the light is emitted, the behavior of the air bubbles in the liquid, and then I will come to my experimental setup and how I can improve it. And at the end, I will try to answer this question about the laser-like emission. So, the sonoluminescence principle. Here, I've put some basic sketch of an experimental setup for sonoluminescence. We here like a frequency generator and an amplifier that creates a static sound wave in the middle. So with this static sound wave, you can trap the bubble in the antinodes of the cavity, and then the bubble will begin to oscillate with the sound wave, and this will when the bubble scratches, it will emit some, like, there will be some really high pressure, and this will make some light. So there are several parameters that influence this sonoluminescence. So first, the amplitude and the stability of your static sound field in the middle. Then the form of the cavity, because this will influence the frequency, the resonant frequency of the, at which you have to make the bubble oscillate. The liquid in which the bubble are the quantity of dissolved air and the particle in the liquid that can influence how the bubble behave, and at the end, the temperature of the liquid. So, first, if you want to have this bubble, you have to trap it. So, and this trapping depends on the primary Bjerknes force, which depends on the volume of the bubble, and if you have the right volume, so the right radius of your bubble, the bubble will be trapped in the antinodes of the static sound field. Then, once you have trapped this bubble, the bubble will begin to oscillate with the with the pressure waves in which it's trapped. So this oscillation is described by the Rayleigh equation here. And so it depends on the gas pressure inside the bubble, on the surface tension of the liquid, the viscosity of the liquid, and obviously the ultrasound, the standing wave of the ultrasound. So here I have the graph of, like, you can see like the solution of this equation, which has been plotted in a paper. You have here the radius of the bubble in micron, the time, and then the acoustic pressure. And what you can see, so here it's for one cycle of the sound, for one period basically. And so what you can see is that at relatively lower pressure you have no sonoluminescence, and from like 1.1 bar approximately you begin to see like this like some burst of light when the like basically you have here the radius increasing when the amplitude of the pressure is negative, and when it becomes to be positive the bubble squeeze, and then there is a lot of pressure, and then here you have a short burst of light from 1.5 to here 1.3 you have this sonoluminescence light. Then the next question is, okay, you have, for high pressure you have a light, but how is this light emitted? So there are several theories for that. Like, let's say will list the two main theory about that. The first theory is that, okay, you have an adiabatic compression, some thermal equilibrium, and because of this very high pressure, the bubble will behave like a black body. So since it's not a perfect black body, it will be what we call a gray body, and this gray body will emit some light, which depends on its temperature. So here we have a temperature of about like 10 to the power of 5 Kelvin. So with the Wien's law, we can determine the maximum wavelengths, like the peak of wavelengths of this emission, and this is like 29 nanometers, so it would be like a peak in the UV. Here you have a spectrum of the sonoluminescence, and yeah, what I've tried to do is some single bubble sonoluminescence, so you can see here it's sort of the shape of the black body spectrum, but in the UV. Then the second theory would be more the theory about a shock wave. So because you have some very high pressure very quickly, you have the creation of a shock wave. So this ionizes partially the gas inside the bubble, the gas being here the argon. And since you have partial ionization, you have plasma, and then this plasma, because like I don't know if you know the Bremsstrahlung effect, but this will create some light, which is made by the what we call the Bremsstrahlung effect. Then now, okay, we know that we've trapped the bubble. We know what like sort of that we have to have some high pressure, but then like we don't know how basically we can come to this sonoluminescence effect. So here you have a diagram showing the radius of the bubble with respect to the amplitude of the pressure of the ultrasound wave. And basically, what you have here is three different branches. One here, like it's some equilibrium branches. One here, which is unstable, or like between 1 and 1.2 for the amplitude of the pressure. 1B at higher pressure, which is stable. And when you come to this branch, you begin to have some chemical reactions. So the air inside the bubble make a chemical reaction. That's basically what is happening is that the oxygen and the nitrogen go make some chemical reaction with the water, so go out of the water, and the argon, which is remaining like in the water, go in the bubble. So we have some increasing of argon in the bubble, and this branch goes like when you reach this branch, you go on the branch C, and on the branch C you have only the argon left. And you have this, and it's here that you have this sonoluminescence effect. And yes, so what is nice is that this branch is stable, so when you reach this point, basically you have your sonoluminescence and it's stable. So what I wanted to do for my experiment is basically, okay, you have a cavity, you are approximately of your resonant frequency, you have a pressure amplitude which is like, let's say, around 1 bar, a little bit more than 1 bar. My resonant frequency for the cavity that I had was around 28 kilohertz, so we are in the ultrasound. Then what we want, like I wanted to sweep the frequency to see like where is the exact resonant frequency, and I can see that if you are at the resonant frequency, the bubble will shrink, and then you increase the pressure, and for the right, basically the right condition, you should have some emission of light. Then, so this was the experiment that I made. So here I have my wave generator, my amplifier, the cavity, a transducer to make the sound wave in the field, in the cavity, and a microscope because I wanted to see basically the bubble. I don't know if you've seen, but the bubble should be like some micrometer size. So I wanted to see it.
You have 1 minute left.
Okay, so this is basically, oh, I don't know, how can I turn the, can I make, no. Yeah, so basically I had some, here's some nice video, but I can't really, maybe, yes. Ah. Yes. So what I managed to do is basically create some bubble in the middle, and then what you can see here, the bubble is creating and goes away of the field. So basically I was not at a stable point in the sound field. So maybe since I don't have time I can go on. So what we think, it was basically we had too high temperature. Yes, this should be vertical, because what you wanted to do is basically have the very stable sound field, and this free shape of the water would sort of like disturb the field, so we want it to be as small as possible. So this should be vertical, and yeah, we have to find a way to create the bubble more efficiently. Then can I finish on that? Okay. So now comes the question of the thermal equilibrium. No, sorry, of the laser-like emission. So basically, based on the two processes of emission of light. If you have thermal equilibrium or if you have a plasma, basically, you don't have some coherent light, because here I have the process that corresponds to the laser-like emission. So you have ground state here, excited state here, and an electron in the excited state, wave coming in, and the wave will help the electron to go to the ground state, and this will then, by the process of stimulated emission, you will have basically creation of two photons that are coherent. So you will have some, they are in the same phase, so you have some coherent emission. And these two processes are basically not the same process as this, and it's some you have some continuous spectrum, so basically this wouldn't work. And even if you had this, you have very low intensity of the light and a peak in the UV, where the maximum of the water absorption is. So you won't have any gain, any efficient gain in your middle, so this wouldn't work. So to conclude, I had my experimental setup, I explained the phenomenon and the important parameter, and I don't think the laser-like emission is possible.
Okay, thank you so much.